quickly do that. Okay. How does the electric potential energy change as the electron moves? So let's say this is kind of open, but our electron potential energy is U equals 1 over 4 pi epsilon naught Q1 Q2 over R 1, 2. So that's the separation between the two charges, Q1 and Q2. If we take Q2 here as our electron, then we could say that this is 1 over 4 pi epsilon naught Q1e of, I should say, minus over R12, because an electron's charge is actually minus e. So then if we plot this, where this is R and this is energy. Turns out they're writing sideways on this. And that's energy, where this is positive energy and that's negative energy. If our charge is positive, then we've got a 1 over R relationship that is negative. And if Q is negative, then we have an 1 over R that's positive, pretending that these two are symmetric, because they should be, as long as the charges are equivalent anyway. And so if Q1 is less than 0, so it's negative, then we have a repulsive force that goes off to infinity as R approaches 0, because it takes more and more energy to force two equally charged particles closer and closer together. But then it goes off to 0 as R goes to infinity. On the other side, if Q is greater than 0, so we have a positive particle, then this goes to negative infinity as R goes to 0, as they want to be as close together as possible. But then the energy still goes to 0 as R goes to infinity. So these two will eventually meet each other as R goes to 0 to infinity. Now if we, so that's one way of looking at it. If we look at the solution here, then the solution is more in the direction of electric field, which is fine. One thing I always find handy for for actually everything, is that the force and the electric field are related. Oh, I should do this. The electric field can become the force with a multiplication by charge. The potential energy goes to force with the multiplication with, I guess, the multiplication of a derivative. Or you can go the other way with an integration. The potential, again, is multiplication by charge, and the potential becomes the electric field with a derivative. So that kind of connects each of these quantities. And so what's in the solution here is then your potential, or I should say this way, is a dx. So your potential is your electric field dx, or dr, I guess. It depends on what distance unit you're using, but if we're just going to consider it one dimension for simplicity here, so your potential is just E dx integral, and then your potential energy is then multiplication by charge, so that it would be Q E delta x. Again, just for simplicity, turning the integral into a delta x, so a change in your distance. And so, oops, I shouldn't have written it like that, but your potential energy this would lead to your potential energy being QE delta x by going this way around this little box, which is also true. But just expressed from the electric field. So if you know the electric field, then you can get the potential energy that way. And all this says is that your potential energy is just whatever your charge is, whatever the electric field you moved the charge through, times delta x. And I guess that would be actually a change in potential energy. So it would be, this would also be a change in potential energy, because you'd have to give it some zero, but you can always assign whatever zero you would like for potential. And yeah, potential energy, and a charge does have potential energy by virtue of its position, which this kind of expresses, but then I think is more simplistically shown through just Coulomb's law. But also if you have not point charges but some electric field, then you could express it like this. And there's many other ways to do it as well. So I would say the solution is correct. The change in potential